So today I'll be analyzing my test, which was half syllabus of fluid mechanics and half syllabus of strength of material. So the first question I am looking at is that the velocity profile for a turbulent boundary layer is given by this for y equals to or less than the shape factor. Now the blunder that I did in the exam was that, as we know that DEM is what is utilized to code that displacement thickness delta star is greater than energy thickness, that is delta double star, which in turn is greater than moment thickness. So that means that H should be equals to delta star, that is displacement thickness, over momentum thickness. This is the actual formula and this is what they asked. But in the exam, what I did was I wrote the shape factor H as theta over delta star. This was the blunder that I did in my exam, and hence I lost a crucial 1.25 marks. So of course the calculation part isn't something that we have to focus on, because that was an easy bit. But since I made a blunder, my ratio came out to be 7/9, which should have been 9/7. So simply I said u by u is y by delta to the power 1/7. We know that displacement thickness is written as nothing but 1 minus u by u dy. That would mean 1 minus y by delta to the power 1/7. We'll be integrating, we'll get integration of dy minus 1 by delta to the power 1/7 y to the power 1/7 dy integration 0 to delta. You'll simply have y 0 to delta to the power 1/7. 1/7 plus 1 is nothing but 8/7, so it will be y to the power 8/7 over 8/7, 0 to delta. That will give me delta minus 1 by delta to the power 1/7. This will become 7/8 delta to the power 8/7. Now delta to the power 8/7, 1/7 simply is 7/7, so that is 1. Therefore the expression will become that displacement thickness delta star is delta minus 7/8 delta. That will come out to be delta by 8, which we often have to remember to save our time. So this is fine. But since the ratio we had to find out, H was delta star by theta, that is momentum thickness, we had to calculate the momentum thickness as well, which is calculated as 1 minus dy. Yes. So it would have simply been minus u square by capital U square dy. And since the profile is given as power 1/7, we would have simply integration 0 to delta y by delta to the power 1/7 dy minus y by delta 2/7 integration dy. So theta will become 1 by delta to the power 1/7, 7 by 8 delta to the power 8 by 7 minus so it will be 7 by 9 1 by delta to the power 2 by 7 and this will be delta to the power 9 by 7 so it will become this will come out to be delta so 7 by 8 delta minus 7 by 9 delta that will be 7 common by 72 delta that is 7 delta by 72 is your theta. Therefore shape factor will be equals to d over m, that is delta star by theta. Instead of theta by delta star, that will be nothing but delta by 8 over 7 delta by 72. That will come out to be 1 by 8 times 72 by 7, so that the answer H comes out to be 9 by 7, which is the B option, whereas I did it wrong. I changed it. So what was my mistake? I, instead of doing d by m, displacement over the energy thickness, so basically we are dividing the largest value by the smallest value, I did the opposite, hence my answer came to be opposite. So this is my wrong. One summarized concept is that the shape factor of a laminar flow is greater than the shape factor in a turbulent flow. That is, the shape factor decreases as flow transitions from laminar to turbulent. Now this is another question where I made a mistake. The mistake I made was because I had solved a question which said that the Reynolds number at a point M in a plate changes from 484 from 100 to 484. It was ESC 2018 question. It was asking about laminar, the laminar boundary layer, but at a fixed point from the leading edge, and due to external reasons the Reynolds number at this spot changed. It changed from 100 to 484, but the point remained same. Since the blasius equation for the laminar boundary layer over a flat flat plate, or the blasius solution for laminar boundary layer suggests that the boundary layer thickness delta is given by 5x over root under Rex, where Re is the Reynolds number, and Rex can be further written as nothing but x over mu, which can be converted into x over mu by rho, which can be written as, where u infinity is free stream velocity, nothing else. Okay, so in this problem of ESC, where the location was fixed, delta 1 by delta 2 is simply written as Re1 by Re2. Because x is same in that case, only delta is varying with the Reynolds number. But in our question in the test, they had asked the displacement thickness at different distance. He told that in the plate, let us assume that at x1 distance we had delta x1, and the Reynolds number at this point was also 8100, but at x2 distance there was delta x2, for which RE2 Reynolds number was 22500. Hence they wanted delta x2 in terms of delta x1. What I did, because I had solved this question, I did not keep this in mind that here the point is not fixed. They have asked at different location rather than one fixed location, as it was in this case. In this case, this formula is correct when x is fixed, then you can use this formula. But when both of these are varying, then what we have to do is delta x1 5x1 over root RE x1. Now root RE x1 or REx can be written as u infinity x1 over nu, and delta x2 can be written as 5x2 over root REx2. Now from here we can write x1 as Rex1 nu over free stream velocity. Similarly, x2 can be written as Rex2 nu over u infinity. Since the flow doesn't mention about anything and the flow is only on that flat plate only, the free stream velocity and the kinematic viscosity for this fluid will be constant. So changing the expression, I can write delta x in general as 5 by root Rex x, and I can write x as Rex nu by u infinity. So I can write, since these terms 5, this and this is constant, I can write delta x directly proportional to Rex over root Rex. That makes the expression delta x is directly proportional to root Rex. Hence in this case, where both x and Rex are varying, delta x1 over delta x2 will be simply equals to Rex1 over Rex2. Hence the situation changes in this case, where x is also varying and Rex is also varying. Here it becomes directly proportional. So now solving the values, we had delta x1, delta x2 we have to find out in terms of delta x1. Rex1 is 8100 and Rex2 is 22500. That comes out to be 90 over 15, that is 18, that is 6. Therefore, have I done something wrong here? Rex1 is 81, that will be 9, and this will be 15. Yeah. Sorry, I can write it as, this can be cancelled, 9 by 15. Therefore delta x2 is 15 by 9 delta x1, that is delta x2 becomes 1.67 times of delta x1. So hence the correct answer would be 1.67, not what I made the mistake. Let's go to the other question. So here is another question where I made a mistake because I was not rather aware of how penstock works and what the term meant. Pressure rise due to water in a penstock depends on. So first of all we'll understand what penstock is, then we'll go about this question. The penstock kya hai? It is nothing but a water carrying pipe which carries water from the reservoir or the surge tank to your turbine or turbine blades. It tolerates the loads on both full load and no load conditions. It is apparently like a pipe, but it is made to bear heavy pressure conditions. Penstocks are installed in such a way that sufficient water depth is always remained at the entrance of the penstock, at the forebay or at the surge tank, so that the air should not enter into the penstock and reduce efficiency of the turbine. Now, as it said that its purpose is to direct the flow from reservoir to the turbines of the hydroelectric power plant. The design is crucial for maximizing the efficiency because it directly affects the water flow rate, the rate through which the water will flow, and the pressure, which in turn influences the power generation. Primary purpose is to transfer water from higher elevation to lower. The potential energy of the stored water is converted into the kinetic energy as it flows. This kinetic energy is used to drive the turbines, and its efficiency depends upon several factors, including the design of the penstock, which are its length and its dia. Both of these factors directly influence its flow rate, that is discharge, and the pressure of the water reaching the turbines. Then it explains why they are important. The length affects the head loss. Due to the friction, longer penstock will have more friction losses, which will reduce the water pressure and flow rate. Properly designing the length to minimize these losses is essential to maintain high frequency. Next is the dia. The dia determines the flow capacity, how much of a discharge, because discharge is area into velocity. Keeping a constant velocity, the more area is there, the more will be your discharge. That is, area can be controlled by the dia itself. So the larger dia, more water to flow with less frictional resistance, which will improve the efficiency. So increasing the dia is, though it increases the cost, but is also gives you an optimal balance. What other additional factors are there? Length and dia are the most crucial ones, but there are also other factors like the material, the shape and its alignment, and the support and the anchors. The material, for its durability and resistance to corrosion and pressure, steel and RC are good options. Shape and alignment, the shape and alignment can influence the flow dynamics. Smooth curves and proper alignment minimizes turbulence and energy losses. Support and anchors, proper support and anchoring of the penstock are necessary to withstand the water pressure. Now we understood what penstock is and what it has to do, but this question asked us which parameters are related to flow in a penstock. It then asks that the pressure rise due to the water in a penstock depends upon. Now the pressure rise in any fluid pipe will increase only when there is a stoppage or water hammer comes into the picture. And when the water hammer is involved, these two terms, that is the density of the water and the elasticity of the water, come in very handy because they directly influence the pressure increase. Whereas water level in the reservoir will have effect on the static pressure or the pressure difference between point A to point B, but there won't be a sudden rise or sudden pressure rise due to the water level in the reservoir. And also roughness of the pipe will only affect the flow profile, and it would not directly come in hand for the pressure rise itself. Hence the correct answer should be 2 and 3, because I did not pay attention to what the question was asking. I thought all of these parameters are somehow related to Penstock. Hence, not reading the question, what the question is asking, has costed me another mark. What we have from Google is that the pressure rise due to water in a penstock, what it is telling you is that sudden transient surge or water hammer pressure rise. So the equation of delta P, that is pressure rise, is related to density, and C is the pressure wave speed, which depends upon the elasticity of the water. Bulk modulus of water is related to elasticity, and the density rho of the water. So these both will affect this term, that is pressure wave, which in turn will affect the pressure rise. So why others were excluded? The water level in the reservoir will govern the steady state of the steady state, that is static head, not the dynamic pressure rise by the valve closure. And the roughness of the pipe will only dampen the oscillation, and it will not affect the peak pressure rise. Hence, elasticity of the water, bulk modulus, which controls the speed of the pressure wave, is important in water hammer. So is the density, and the roughness of the pipe is not something that will affect the pressure. So here is another question in which I made a mistake. So the question was that assertion reason: water flows through a pipe connecting two reservoirs. The line joining the water surface levels in the reservoir is the hydraulic gradient. Now I was not sure about, or I had not revised hydraulic gradient, so I was not aware about the behavior of hydraulic gradient, especially whether it touches the water surface level or not. On that doubt, because of this doubt, I assumed this as to be wrong. I presumed that since I have seen something like this happen, this is where the hydraulic gradient line goes, something like this, I presumed that it must be just above the water level in the reservoir, which was wrong. Now, the reason is that there will be no negative gauge pressure anywhere in the pipeline as long as the pipeline lies below. This one point I was sure about, that below the hydraulic gradient, the HGL or the hydraulic gradient line, your pressure will always be positive, and it's only above it that the pressure gets negative. So I was sure about the reason, so this part is correct. Hence I went up with A is false but R is true. But since this is correct and this is also correct, but these two are not related, the correct answer would have been B. Now let's see into the concept. First thing first, hydraulic gradient line represents the variation of piezometric head, which is P by rho plus Z, that is pressure head plus the datum head. It does not include the velocity head, that is part of the total energy line. That is why total energy line and the hydraulic gradient, they both are separated by a kinematic head. It is an important concept in fluid mechanics and hydraulics, typically used to determining pressure variations. The difference has been told. It is important in the design of the pipelines, OCF, and water distribution. So, at the starting point, the hydraulic gradient line matches with the free water surface level of the reservoir. And at the ending point, it also matches with the free water surface level of the receiving reservoir. In terms of direction of its slope, it always slopes downwards in the direction of flow because of the friction creates or friction losses given by Darcy, FLV square by 2GT. It is always parallel to the hydraulic gradient line, to the total energy line with a vertical gap of V square by 2G. If HGL is above the pipe center, the pressure is positive, and if HGL dips below the pipe center, the pressure would be negative or vacuum. The core concept itself is Bernoulli's theorem, where the total energy per unit weight is given by P by rho G V square by 2G plus Z, which is the datum head, where pressure head is P by rho G, and kinetic head is v square by 2g, and the datum head is elevation, and piezometric head is pressure plus datum head. So what it says is, why is the assertion true? Because the large reservoirs have open free water surface exposed to the atmospheric pressure, and at these pressures the gauge pressure is 0, hence this term comes out to be 0. Thus the total piezometric head at the both ends of the pipe strictly matches the respective pool elevation z. If this is z, hence the hydraulic gradient line will match with the water level surface in both top and bottom. Hence straight line drawn between these two water lines maps the progressive linear drop caused by the friction. The second is that this is your P by rho g, which can be written as hydraulic gradient head minus the pipe's center elevation. What it says that if your hydraulic gradient head is above then pipe center elevation, then you will have a positive pressure. But if it is, the pipe center line is above, then this will increase and this will be below it, it will become negative, so the vacuum pressure, and exactly at the HGL line the atomic pressure would be 0. And why is reason not the correct explanation? Because assertion focuses on defining the hydraulic gradient line for a two reservoir system based on the boundary condition, whereas the reason is discussing an application or the consequence of the hydraulic gradient line's spatial behavior. Because reason states a completely distinct engineering principle rather than explaining why the reservoir boundary conditions, surface boundary condition form the HGL boundaries, it is categorized as true statement but not its correct. So clearly ये एप्लीकेशन है हाइड्रोलिक ग्रेडियंट लाइन का. So this is how hydraulic gradient line varies when there is a flow in two reservoirs at different elevation. The dotted line is your hydraulic gradient line and this is our pipeline. We can clearly see when the pipeline is above the hydraulic gradient line. When it is above the hydraulic gradient line, the pressure becomes negative. This is our pipeline. Pressure becomes negative. Whereas when the pipeline is below the hydraulic gradient line, we have pressure as positive. And on the free surface of the reservoirs, we can see the hydraulic gradient line is intersecting the water surface or the free surface. Let's see another question. Another question in which I made a blunder was this: that two tanks are connected in parallel by two pipes A and B which have identical friction factors and lengths. If suddenly, let us say this was our diagram, supposedly this is tank 1, this is tank 2, this is pipe A and this is pipe B, and what they are saying is that they had identical friction factors and same lengths also. Suddenly they have doubled the size of A, that means the dia has been doubled, then the ratio of discharge would be. Now you see, the concept is simple, that in a parallel flow between two reservoirs, the head loss is equal, and from Darcy Weisbach equation in terms of discharge, Darcy Weisbach equation in terms of the discharge, we have HF equals FL square by 12.1 d to the power 5. So simply I could do that H1 is equals to, or since head loss in both cases is same, and so is friction factor and length, and this is constant, so the only thing varying would be q1 square or qa square by da5 equals qb square by db5, and instead of using square in my test I simply used qa and qb. I did not noticed square. So that is, since they have asked us the ratio qa by qb, qa square by the dia of A has been doubled, qb square is d, this makes qa by qb whole square equals to 32, which was the option number D. qa by qb will be root under 32, which will be roughly equals to 5.66. Hence the correct answer is 5.66. Here is another question based on the Darcy Weisbach equation, where it says that friction factor was misjudged by 20%. Then for this case, the error in estimating discharge. First of all, I was not aware about this concept, how these two are related. But since the formula we have is the head loss is taken as FLV square or FLQ square by 12.1 d to the power 5. For a constant head, we can say that Q square is inversely proportional to the friction factor, or one can say that discharge is inversely proportional to half, or discharge is directly proportional to minus 1 by 2. Now using log, I can say ln Q is minus 1 by 2 ln F plus constant. Differentiating to find the proportional error, I can write it as dq by q equals minus 0.5 df by f, since differentiation of ln f will be 1 by f. So this will give us our relation. Now it is said that error in friction factor, that is df by f, is positive 20%. Therefore error in discharge will be dq by q equals minus 0.5 times 20%. That gives us minus 10%, which tells us the answer is D. What it tells us is that when you overestimate the friction factor, in this case it was by positive 20%, this leads to overestimating pipe resistance than what actually it is, which leads to the underestimation of the discharge. By 10%. That is, you are accounting for a discharge which is lesser by 10%. Here is another question which tells us about the loss of head due to sudden expansion. Now the head loss due to sudden expansion is given by V1 minus V2 whole square by 2g, but in this question there was misprint. It should have been this, hence the correct answer would be C. Yes, the previous question was dependent upon the concept of minor losses in pipes. We'll just quickly revise it. The loss due to sudden expansion, it is a type of minor loss at the end of the pipe when smaller dia pipe meets a large dia pipe due to sudden enlargement in the area of the flow, and this loss is larger than the loss due to sudden contraction because eddies are formed at the entrance of a large diameter pipe. That is, at the entry you see eddies here. The formula is given by head loss equals bracket V1 minus V2 whole square by 2G, which can be evaluated into this form using the continuity equation. V1 square by 2G bracket 1 minus A1 by A2 whole square. Then comes loss due to sudden contraction. It is a type of minor loss where large dia pipe meets small dia pipe, or small dia pipe is attached to water reservoir due to sudden decrease in the area of flow. In this, separation of flow occurs at the entrance of small dia pipe. This is where the separation is. This can be calculated as HL V1 whole square by 2G. This is your area A2, and this is your area or the position of vena contracta. As you can see, only A2 and AC are being involved here. A1 is not being involved here. So it will be A2 by AC minus 1 to the power whole square, or we can write it as V2 whole square by 2G 1 by CC minus 1. CC is generally velocity at the vena contracta by the velocity before. CC is area of the vena contracta by the area before it. Then minor losses caused by disruption of the flow due to installation of appendices, valves, bends. This involves the expression loss coefficient, which is also called as resistant coefficient. It is defined as ratio of head loss or loss of head to the kinetic head. It is saying that in some cases minor losses may be greater than the major loss in case where there are several turns and valves in short distance, and these are the types: loss of energy due to sudden enlargement, sudden contraction, entrance of the pipe, exit from the pipe, wherein entrance of the pipe is similar to sudden contraction and exit is similar to sudden enlargement, and then there is bend and pipe fittings. This is V square by 2G 1 minus A1 by A2 whole square. Then sudden contraction V2 square by 2G 1 by CC minus 1 to the whole square, and in case CC is not given, HL is 0.5 V2 square by 2G. Then loss at the exit of pipe is simply V square by 2G, and loss at the entrance to the pipe is 0.5 V square by 2G. You see, what happens is, since it is similar to the sudden expansion, and what happens is that V2 becomes 0 at exit. So this simply becomes V1 square by 2G. And loss due to bend is given by kV square by 2G, kV square by 2G, where k is 1.2 for a 90 degree bend like this, and for a 45 degree 10 it is 0.4. so these two values are important. So this was the concept behind the minor losses. Let's move on to the next question. Here we have another question which said that the lower critical Reynolds number for a pipe flow is well defined at, this is not 2.00, this is 2000 only. So the lower critical Reynolds number for a pipe flow is well defined at 2000, while the upper critical number has been found to exceed even 4000. So we know that for Reynolds number up to or less than 2000 we have laminar flow. In between 2000 to 4000 we have a transition flow, and above 4000 we have turbulent flow. What the question was saying is that the lower critical number for pipe flow is well defined at 2000, and while the upper critical number has been found to exceed even 4000. Then it said when the Reynolds number increases above that of lower critical value, the transition tends to depend on the external disturbance. Now I was not sure about how could external disturbance affect the transition, and how the Reynolds number can increase above the lower critical value of 2000. Let us say this is our Reynolds number, this is 2000, this is 4000. Above this we have turbulent, below this we have laminar, and in between we have transition phase or transition flow. Now since I was skeptical about the external disturbance, I chose reason as false, and I was somewhat confirmed about the assertion. But to my dismay, what the question was actually, the concept behind was that for a fluid flow through a pipe, the laminar flow always transitions to turbulent flow around a lower critical Reynolds number of 2000. Below this value, any disturbance is naturally damped out, and conversely, the upper critical Reynolds number is highly variable. If the pipe is exceptionally smooth and external disturbances are minimized, the laminar flow can be maintained to values exceeding 4000. That is, you can maintain a laminar flow up to a Reynolds number of 4000 if you control the external factors. Then the reason was asking that when the Reynolds number exceeds the lower critical value, the flow enters a transitional regime, which is fine. In this zone, whether the fluid stays laminar or becomes turbulent depends heavily on the external factors. Yes, after your RE has exceeded 2000, whether it stays laminar or it becomes turbulent will heavily depend upon the pipe roughness, vibrations, or any initial fluid disturbances. If there are no disturbances or external factors, the flow remains laminar up to a much higher upper limit. Hence, reason is also true. Now, is there any relation between the assertion and reasoning? The upper critical Reynolds number can reach high values precisely because of the transition past 2000, which depends entirely on the minimizing external disturbances. Thus, reason provides the correct physical justification. Assertion was asking us that the critical Reynolds number to maintain laminar flow for pipe inside the pipe is well defined at 2000, and the upper critical Reynolds number can even exceed. What critical meant here was maintaining the laminar flow, which I was not aware about. So when Reynolds number increases above that of the lower critical value, the transition tends to depend upon the external disturbance. Hence, both these are relating. वो क्रिटिकल Reynolds नंबर 4000 तक भी जा सकता है सिर्फ तब और तब जब ट्रांजिशन जो है वो एक्सटर्नल डिस्टर्बेंसेस पे डिपेंड करती है. तो दोनों एक दूसरे को कॉम्प्लीमेंट कर रहे हैं. Hence, this is correct. Here is another question where I was not, since I had not revised the turbulent flow chapter, I was not able to do it. It said that the velocity measurement of a flow through a rough circular pipe indicated that the average velocity is 2.6 meter per second, and the center line velocity, which is also referred as Umax, was given as 3.17 meter per second. Then it asks about the friction factor. Now there is in turbulent flow in circular pipes, there is velocity defect law, which relates Umax and U and the shear velocity, where it's is given as u max minus u bar by u star as 3.75, where u star is shear velocity. U max and u bar we had to find out the shear velocity. Shear velocity u star I can find as u max minus u bar by 3.75. That will be 3.17 minus 2.6 by 3.75. That will come out to be approximately 0.152 meter per second. Then we had to relate shear velocity to the friction factor, which जो हमें निकालना है. तो u star is equals to u bar f by a. This is the relation between the shear velocity, the mean velocity, and the friction factor. U star, we have the u star, that is shear velocity, and we also have the mean velocity. We just had to find out friction factor. This will come out to be 0.027. Hence A is the correct answer. So these two formulas were involved. I was not aware of these because I had not revised turbulent flow. Let's move on to the next question. Here we have another question. This is actually a PYQ of engineering services 1998 or 1996, and it said which of the following condition would entail a greater energy dissipation in the turbulent flow. The first one was smaller eddy size, the second one was lower viscosity, and third one was large intensity of turbulence. Now the question is asking about which would entail a greater energy dissipation in a turbulent. Of course, large intensity of turbulence would dissipate more energy. I was sure about third, but I was doubtful about the first statement and the second statement. I believe that instead of smaller eddy size, I believe larger eddy size will yield greater energy dissipation, but unfortunately that is not the case. The concept is that the energy dissipation in turbulent flow is mainly due to the conversion of kinetic energy of large eddies through viscous forces acting at smallest scales, that is smallest eddies. What smaller eddy size means is that the turbulent kinetic energy is transferred to smaller scales where viscous forces are more effective, and the increase of rate of energy dissipation, the smaller eddies increase the rate of energy dissipation because viscous dissipation occurs at the smallest scales. कहने का मतलब कि smaller eddy size में ज़्यादा energy dissipation होता है rather than the large eddy sizes. Then second point was the lower viscosity. In this, viscosity is the property responsible for dissipating energy. First, lower viscosity means that there is less resistance to flow, hence less energy dissipation. Hence lower viscosity पे कम energy dissipate होगी, whereas higher viscosity पे ज़्यादा dissipate होती. Hence this was not correct. So the only option was 1 and third, that is B. Higher turbulence से तो ज़्यादा kinetic energy होने के कारण ज़्यादा dissipation होना ही है. So I can say that smaller eddy sizes and large turbulence intensity would lead to greater, whereas the lower viscosity will lead to less energy dissipation. Here is another question which says shear velocity is, this is a SSC PYQ, and is it a non-dimensional quantity? No, it has units of meter per second. The velocity of fluid at the edge of the laminar sublayer? No. Then it is a fictitious quantity? Yes, because it does not represent any actual physical quantity, physical velocity. The velocity of fluid at the edge of roughness element? No. So you see the shear velocity U star is given as square root, where tau naught is the boundary shear stress and this is the fluid density. Why is it fictitious? Because even though its units are meter per second, which are of a velocity, but it does not represent any actual physical velocity of any fluid particle in any fluid flow. So it is a purely mathematical construct which is used to represent the shear stress in velocity terms, making it a fictitious quantity. Then next concept is, with increasing aging of pipes, the proportion between the maximum velocity and the mean velocity, how does it changes? So there is this relation U max by U bar is equals to 1 plus 1.33 root under F. This is for turbulent flow pipe or turbulent pipe flow. Now, as the pipe ages, there scaling hoti hai usme, there is corrosion and there is deposit, which increases the roughness of the pipe wall. And how does it affect the friction factor? We know that friction factor is dependent upon the relative roughness, K by D ratio. So as K increases, friction factor also increases. And as friction factor increases, this proportion increases. And hence, the concept is that when higher roughness comes in the pipe walls, it slows down the fluid near the wall or close to the wall. And it leads to relative increase in the central velocity U max to maintain the same discharge. Hence, with increasing age of the pipes, the proportion between the maximum velocity and mean velocity increases. Here is another question in which I fell in the trap that the flow through very narrow passage would be the turbulent flow. But the concept is not about whether the cross section is less or high. Well, it is actually, but the core thing is how the Reynolds number is involved. So the concept is that whether the flow remains laminar or turbulent will be determined or governed by the Reynolds number, which is rho Vd by mu. And if you have a high Re, there will be inertial forces will dominate the turbulence, and if it is lower Re, then viscous force will dominate, hence laminar. We know that Reynolds number is given by inertial force over viscous force. So when the viscous force dominate, Reynolds number decreases and the flow tends towards the laminar, and opposite happens. When the opposite happens, the flow goes to the turbulent. In this question, keeping all the aspects same, Reynolds number is directly proportional to the dia of the pipe. So that means for higher or a large passage which has a higher dia, the Reynolds number will be higher, hence the flow will go towards turbulent. Hence turbulent flow generally occurs at low velocities, no. In highly viscous, no. More viscosity means more viscous forces, and hence Reynolds number will be less. Through narrow passages, no, dia is less, Reynolds number will be less. And at high velocities, through large passages, because not only would it increase velocity, high velocity, the dia is also increasing, keeping the nu same, hence D will be the correct answer. Here is another question which was asking about the incorrect or not correct statement. The question was based on the concept of the Nicorates roughness regime, where we know that within a turbulent flow or turbulent zone, there is always the laminar sublayer thickness denoted by delta dash. And we know in a hydrodynamically smooth boundary the average projections are given by K. Average projection की height K से show की जाती है. And for hydrodynamically smooth pipe के लिए this ratio of K by delta dash is less than 0.25, whereas for a rough pipe, hydrodynamically rough pipe, K by delta dash is greater than 6. Because in that case what happens is, ये हमारा turbulent zone है, and let us say that this is our laminar sublayer within the turbulent zone, laminar sublayer. This is delta dash, but in this case the roughness is high, so the average height K of the vertical projection is high, hence K by delta is greater than 6. और इन दोनों की जब range इन दोनों के बीच में हो, then you are in a transition zone. Hence पहला स्टेटमेंट कह रहा था कि हाइड्रोडायनेमिकली स्मूथ बाउंड्री लेयर्स में थिकनेस लैमिनार सब लेयर की कम है रफनेस प्रोजेक्शन से, बट ये स्टेटमेंट गलत है, बिकॉज हाइड्रोडायनेमिकली स्मूथ बाउंड्रीज में लैमिनार सब लेयर की थिकनेस ज़्यादा होती है रादर देन द रफनेस प्रोजेक्शंस. हेंस दिस स्टेटमेंट वाज रॉन्ग. द करेक्ट आंसर वुड बी ए. हियर इज अनदर क्वेश्चन which was from the turbulent flow, and since I had not revised turbulent flow, I went for the bait. Question was asking that the maximum velocity is um and the mean velocity is u and shear velocity is this. Then in case of turbulent flow through circular pipe, it is related as this ratio is equals to what? Now we must know the concept which I was, since I had not revised turbulent flow, that the velocity distribution for turbulent flow, the velocity distribution for turbulent flow in a pipe at a distance y from pipe wall, let us say this is our pipe and we have y from, this is our r, sorry, then let us say this is at center we will have u max. The general expression is that any velocity u, local velocity at any distance y, minus u bar, where u bar is the mean velocity, over u star, that is shear velocity, this is equals to 5.75 log y by r plus 3.75. This is the general expression, where u is local velocity at distance y, u bar is your mean velocity, and u star is the shear velocity, where u star is taken as f by 8. Now at the center of pipe y becomes r, therefore this relation, and u local velocity becomes u max, so the relation becomes u max, u bar can be written as um also, as in our question um is the mean velocity, minus um by u star will become 5.75 log, since y is r by r plus 3.75, log 1 is 0, so this relation becomes u max minus um by u star equals 3.75. And since this formulation relies strictly on the velocity profile, सिर्फ y पर depend किया, hence this value of 3.75 is universally applicable to both smooth and rough boundary flows. Hence our relation um minus u, where mean is u, over shear velocity, this is equals to 3.75 for both smooth and rough, and C is the correct answer. Here is another question which says that flow in the boundary layer is always laminar, which is a wrong statement. Reason says that in turbulent flow on a smooth boundary, a laminar sublayer still exists. Exactly. You see, over a flat plate, we know that the boundary layer develops like something like this. Then comes the transition zone, and then comes the turbulent zone. Now within this turbulent, this is our boundary layer. Within this turbulent zone, there always exists a laminar sublayer जिसका थिकनेस डेल्टा डैश होता है, और वो एग्जिस्ट करता है चाहे रफनेस स्मूथ हो या रफ हो, पाइप की वॉल स्मूथ हो या रफ हो, इट विल एग्जिस्ट नो मैटर व्हाट इन द टर्बुलेंट जोन ओनली और टर्बुलेंट फ्लो. सो फ्लो इन द बाउंड्री लेयर इज ऑलवेज लैमिनार. दैट इज रॉन्ग बिकॉज बाउंड्री लेयर में 3 जोन्स आते हैं, तो फ्लो लैमिनार भी रहता है इफ इट इज लेस देन 5 into 10 to the power 5, and it becomes turbulent if it is greater than 5 into 10 to the power 5. So this was wrong, and the second statement is correct, that laminar sublayer still exists in the turbulent flow. Hence A is false but R is true. So here is another question in which I fell for the trap because of the reason that I had kept this in mind from the blasius equation, that for a laminar flow, delta was given as 5x over root rex, and for your turbulent flow, delta was given as 0.376 by rex to the power 1 by 5, and the variance was delta is directly proportional to x to the power 1 by 2 in laminar, and delta was directly proportional to x to the power 4 by 5 in the turbulent flow. So instead of focusing on what the question has asked, the question has itself asked for not delta but delta by x. Hence in this case, and since it was the turbulent boundary layer, delta is directly proportional to x to the power 4 by 5 into the turbulent flow, but the question was asking delta by x, which would have been x 4 by 5 over x. That would give you x to the power minus 1 by 5, I presume. Yes, that is delta by x. This term is inversely proportional to x to the power 1 by 5, which I can take as 0.2. Therefore, as x increases, delta by x will decrease. Hence, instead of it increasing with the distance, it will decrease. So another blunder that I made in the test. Hence it is very important to see what the question is asking. Here is another question based upon the Magnus effect. The Magnus effect क्वेश्चन पूछ रहा है कि मैग्नस इफेक्ट को यूज़ करके हम चाहे क्रिकेट हो, टेनिस हो या टेबल टेनिस हो या गोल्फ हो, लिफ्ट ऑब्टेन करने के लिए एक ऐसी बॉल में जिसका ट्रेजेक्टरी कुछ ऐसा मूव कर रहा है फ्रॉम लेफ्ट टू राइट, हाउ विल वी लिफ्ट दिस बॉल? तो पहली चीज़ तो लिफ्ट होगी वर्टिकल प्लेन में इस सिचुएशन के लिए. एज्यूमिंग एक बैट्समैन ने शॉट मारा और आप साइड ऑन व्यू से देख रहे हैं और बॉल का ट्रैजेक्टरी कुछ ऐसा है जैसा कि हमें यहाँ दिख रहा है. सो ऑफ कोर्स ग्रेविटी के कारण ये बॉल इवेंचुअली नीचे आएगा जैसा कि होता है प्रोजेक्टाइल का मोशन. पर इस क्वेश्चन में वो कह रहा है कि किस तरह से हम लिफ्ट अटेन कर सकते हैं, उसके लिए नेचर ऑफ स्पिन क्या होगा बॉल का। तो जो बॉल ऐसे मूव कर रहा है फ्रॉम लेफ्ट टुवर्ड्स राइट, तो एयर फ्लो हमेशा उसके अपोजिट लगेगा। तो दिस इज द डायरेक्शन ऑफ द एयर फ्लो। नाउ वी हैव टू, जब भी हमें लिफ्ट चाहिए होता है तो हमें बॉल के जस्ट ऊपर हाई वेलोसिटी, लो प्रेशर, और बॉल के नीचे लो वेलोसिटी, हाई प्रेशर मेंटेन करना होता है। ये एरोफॉइल्स के साथ भी है, एरोप्लेन के लिफ्ट के साथ भी कॉन्सेप्ट सेम है। हाई प्रेशर बॉल के नीचे और लो प्रेशर बॉल के ऊपर। तो हाई प्रेशर से लो प्रेशर जो है एक फोर्स लगेगा परपेंडिकुलर टू द फ्लो ऑफ द एयर, लिफ्ट, जिससे कि बॉल आपकी लिफ्ट करेगी, बहुत जल्दी नहीं आएगी और इसकी ट्रैजेक्टरी में फ़र्क आ जाएगा। अगर पहले कुछ ट्रैजेक्टरी ऐसी थी तो अब ट्रैजेक्टरी कुछ ऐसी होगी, या रिलेटिवली राइज आएगा उसमें। तो इसके लिए नेचर ऑफ स्पिन कैसा होना चाहिए वर्टिकल प्लेन में, क्योंकि लिफ्ट हो रही है तो वर्टिकल प्लेन में देखेंगे स्पिन की नेचर को। अगर हम एंटी क्लॉकवाइज देते हैं तो यहाँ पे वेलोसिटी होगी v टर्मिनल, और इसी डायरेक्शन में एयर का ड्रैग लग रहा है तो नेट वेलोसिटी इंक्रीज होगी, हैंस यहाँ हाई वेलोसिटी। पर अगर यहाँ देखें तो क्योंकि एंटी क्लॉकवाइज नेचर है तो यहाँ पर वेलोसिटी होगी बॉटम पे vt, बट एयर ड्रैग ऑपोजिट डायरेक्शन में है तो यहाँ पर नेट स्पीड को अगर हम देखें, इफ़ यू सी द नेट स्पीड, तो नेट स्पीड यहाँ ज़्यादा है और नेट स्पीड यहाँ पर रिड्यूस्ड है। हेंस यहाँ पर हाई वेलोसिटी है, जहाँ पे वेलोसिटी हाई रहती है वहाँ प्रेशर लो रहता है, और जहाँ पे वेलोसिटी लो रहती है वहाँ पे प्रेशर हाई रहता है। तो हाई प्रेशर से लो प्रेशर एक फोर्स लगेगी, विच विल बी योर लिफ्ट फोर्स, जो कि बॉल को लिफ्ट करेगा। हैंस इस क्वेश्चन में एंटी क्लॉकवाइज स्पिन होगा इन द वर्टिकल प्लेन। नाउ लेट्स सी हॉरिजॉन्टल प्लेन में जो हमारा साइडवेज मूवमेंट होता है, जो कि फुटबॉलर्स अक्सर यूज़ करते हैं, रोनाल्डो एंड ऑल ऑफ देम, वहाँ पे मैग्नस इफेक्ट कैसे काम करता है। ये हमारा कोर्ट है इस फुटबॉल का, कुछ ऐसे, और ये हमारा गोलकीपर यहाँ खड़ा हुआ है, और ये बॉल है हमारा, मान लो मेसी या रोनाल्डो पेनल्टी ले रहा है, मुझे फुटबॉल के वैसे रूल्स तो पता नहीं है। लेट अस सी इन दिस केस, अगर मैं बॉल के सेंटर लाइन से एक लाइन ड्रॉ करूं तो ऐसा लग रहा है कि अगर बॉल सीधा जाएगी तो कोर्ट पे तो नहीं जा रही, कोर्ट के अंदर या नेट के अंदर तो नहीं जा रही, बट मेसी को इस बॉल को कुछ ऐसा हिट करना है कि वो इस पॉइंट पे एक टर्मिनल वेलोसिटी देकर एक एंटी क्लॉकवाइज स्पिन दे दे इसे हॉरिजॉन्टल प्लेन में, जिससे कि क्या होगा, यहाँ से आपका एयर ड्रैग लग रहा है, यहाँ पर एयर की वेलोसिटी से अपोज करेगी और यहाँ पर वेलोसिटी से जो है सपोर्ट करेगी। तो इस केस में यहाँ पर हाई वेलोसिटी हो जाएगा और यहाँ पे लो वेलोसिटी, जहाँ पे वेलोसिटी हाई वहाँ पे प्रेशर लो, और जहाँ पे वेलोसिटी लो वहाँ प्रेशर हाई। हेंस एक साइडवेज फोर्स लगेगा यहाँ पे हाई प्रेशर से लो प्रेशर, जो कि बॉल की ट्रैजेक्टरी को इंस्टेड ऑफ गोइंग स्ट्रेट मूव कराएगा कुछ ऐसा कि वो स्ट्रेट ना जाते हुए गोलकीपर के नेट पर लगेगी। हेंस वो सीधा ना जाकर कुछ ऐसे साइडवेज कर्व लेती है और गोल हो जाता है. तो दिस इज़ द होल कॉन्सेप्ट ऑफ मैग्नस इफेक्ट, जहाँ पे आप वर्टिकल प्लेन में स्पिन देकर उसे लिफ्ट करवा सकते हो वर्टिकल प्लेन में, और हॉरिजॉन्टल प्लेन में भी उसे स्पिन कराकर साइडवेज मूवमेंट कर सकते हो. हेंस दिस इज द कॉन्सेप्ट. Here is another question which says that for flow under a sluice gate where the upstream depth is 1.2 meters, the upstream depth is 1.2 meters and the downstream depth is just 0.3 meter at the Wiener contractor. So discharge per unit meter width per 1 meter width would be, you see, in this question two concepts are involved. One is the continuity equation and the other one is the specific energy concept. At the upstream of the sluice gate, due to higher depth, the velocity will be lesser, and just below the gate where Wiener contractor forms in the downstream will have a higher velocity and lesser depth. So maintaining both the specific energy conservation, assuming that there is no friction loss, and continuity equation, we'll have two equations to solve this question. First one is A1 V1 equals A2 V2, and the other one will be E1 equals E2, that is Y1 plus V1 square by 2G equals Y2 plus V2 square by 2G. And since we have to find out discharge, so what we will do is we will substitute. Let us put V1 equals since I can write this as B dot Y1 equals Q, or V1 Y1 equals Q by B or Q. Similarly, I can write that V2 Y2 equals Q, or I may write V1 equals Q by Y1 and V2 equals to Q by Y2. Putting in this equation second, I can write Y1 plus V1 square, that is Q square by Y1 square 2G equals Y2 plus Q square by Y2 square 2G. Let's match the like terms. We'll have Y1 minus Y2 equals Q square by Y2 square 2G minus Q square by Y1 square 2G. Y1 minus Y2 equals Q square by 2G is common. We'll have Y1 square minus Y2 square by Y1 Y2 square. Y1 minus Y2, we can write A square minus B square as Y1 minus Y2 times Y1 plus Y2, Y1 square Y2 square. This will get eliminated. So eventually we'll have Q square equals 2G Y1 Y2 whole square over Y1 plus Y2, which is required, or we can use this formula directly to save our time. This will become this becomes Y1 Y2 root under 2G, or I can write it as over Y1 plus Y2, where Y1 is upstream depth of water and Y2 is downstream. In our given question, Y1 is 1.2 meters and Y2 is 0.3 meters. And on solving, I can write 1.2 times 0.3, that becomes 0.36 Y1 Y2. This is approximately 19.6 over, adding these both, 19.6 divided by 1.5 gives 13.06. If we square root, this becomes 0.36 times 3.614 and it gives us roughly 1.30. Therefore, the answer is discharge per unit width becomes 1.30 meter square per second. Hence, the correct answer would be, since the closest option is 1.5, we'll have to go with 1.5 only. Let's see the next question. Here is another comparison based question, where it says that two small orifices A and B of dia 1 cm and 2 cm are respectively placed on the sides of the tank at depth H1 and H2 below the open liquid surface. If the discharge is equal, we know the discharge actual in a orifice is given by CDA into root 2GH, where velocity is given by root 2GH. Therefore, they have also mentioned that if the discharges are equal, then the ratio of H1 by H2, assuming CD. So clearly, if CD is constant and dia is given, so the only two parameters working here are, or Q is directly proportional to, since area is pi by 4 d square, where pi by 4 is constant, I can simply say it is directly proportional to d square and root h, because root 2g is also a constant. So I may write Q1 equals Q2, that will be d1 square root h1 equals to d2 square root h2. For A, the dia is 1 centimeter square, so I can write 1 square. For A, the depth is h1, and for B, the dia is d2, 2 centimeter square. What I have to find out is root h1 over root h2 equals, that will be 4 by 1. Therefore, h1 by h2, which is what the question has asked us, will be 16 by 1. Hence, A is the correct answer. Here is another question which says the coefficient of velocity of an orifice is given by, one should remember this directly, and it simply means, let us say this is our reservoir or tank with a head H. This is the water filled, and this is how the water is coming out of it at distance x, and this is the difference y. Then the coefficient of velocity is given by Cv equals root under x square by 4yh, which amounts to x by 2 root yh. Hence, A is the correct answer. Here is another question which says that consider the following types of weirs. For all these weirs, the values of exponent is in the formula Q equals K h to the power n, where K is a constant. The correct sequence of these weirs in the increasing order of the value n. The first one is the proportional weir or the Sutro weir, which has an image of something like this. And for this we have Q equals K h to the power 1. This is our Sutro or proportional weir. The second one is Cipolleti weir. It is a trapezoidal weir with the formula of discharge 2 by 3 CD L root 2G h to the power 3 by 2, where the slope is given as 1:4, where we have 1 horizontal and 4 vertical, and the angle is probably 28 degrees. The second, so the power becomes 3 by 2. That is, for Cipolleti it is not 5 by 2 but 3 by 2, that is 1.5. For this the power is 1. For a parabolic weir, the n value is 2, so it is 2, and then for a rectangular weir it is 3 by 2, that is h to the power 3 by 2. So the in increasing order, what will be the sequence? So of course the smallest is 1, followed by we have Poissuelli, which has 1.5, and then we have a rectangular also, which is 1.5, that is 1, 2, 4, and highest power is 3 with parabolic weir. So therefore correct order is 1, 2, 4, 3. Here we have another question on the basis of alpha, that is the kinetic energy correction factor. But since the question has asked for extensive stationary plates, I simply relied on my memory and I ticked 2.0, but that is not for the extensive stationary plates. You see, this is alpha and this is beta. This is our kinetic energy correction factor, and this is momentum correction factor, and these values are different for the different cases. The first case would be is that of circular pipe. The second case is that of parallel plate, and then we have turbulent case. So alpha for a laminar flow is given by 2 in a circular pipe, and beta in a laminar flow is 1.33. For a parallel plate laminar flow, again alpha is 1.543 and beta is 1.2. For a turbulent flow it is 4 by 3 and beta is 1.2. Therefore in this question where laminar flow was taking, the correct answer would have been 1.543, that is B. This would have been for a circular pipe, and this is for parallel plates. Hence B is the correct answer. Here is another famous question which is often asked, that in a steady laminar flow of a liquid through a circular pipe which has an internal dia D and is carrying a constant discharge, the hydraulic gradient is inversely proportional to. So you see, the concept is that in the Haigen Poissuelli's head loss formula, we have HF equals 32 mu VL upon rho GD square. By just looking at it, one can think that HF is inversely proportional to D square, but that is not the case, because inside V is D hidden, because for a constant discharge Q is AV and it is a circular pipe. We can write, therefore V becomes Q by pi by 4 D square, which makes it equals to 4Q by pi D square. We substitute in the formula and our formula will become 128 mu QL over pi rho G D to the power 4. Therefore the variation is HF is inversely proportional to D to the power 4. So C is the correct answer. Let's move on to the next question. Here is another question, an important one rather, which helps you to understand the difference between two chapters, laminar flow and the turbulent flow, which unfortunately I did not revise well. But here's the question, which says that for laminar flow in a pipe carrying a given discharge, the height of the surface roughness K is doubled to 2K, and in such case how will the Darcy Weisbach friction factor be changed? So one has to understand the concept that while you remain in the laminar flow, as long as we are in the laminar flow, the friction factor is given by 64 by Re, and this Re in laminar flow is not dependent upon the pipe wall roughness K or dia of the pipe. So as long as it is in the laminar flow, the friction factor is just dependent upon the Reynolds number and not how the reference changes. But when you are in the transition or the turbulent flow, there comes the Moody's chart where friction factor is dependent, or you could say a function of K by D. Hence there things will be different, but in this case it will remain unchanged. Hence A is the correct answer. Let's move on to the next question. So here are two questions. The first one is that if the velocity profile is parabolic, assuming that y by delta, if the velocity profile is, let's say, 2 eta square minus eta or 2y square minus y, then the shear stress profile, since tau is mu du by dy, once you differentiate du by dy, you will get 4y minus 1. That is, it will be a straight line or a straight profile. So C is the correct answer. Let's move on to the next question, which says that water has a kinematic viscosity, because units are centistoke. It has a kinematic viscosity of 1 centistoke. 1 centistoke is equals to 10 to the power minus 6 meter square per second. And critical flow, where it is asking the dia is 1 centimeter, that is D is 1 centimeter, which is nothing but 0.01 meter. It is asking that the critical flow will corresponding to the discharge of, you see, in a pipe critical flow occurs at REC, that is Reynolds critical, as 2000. We know the formula relating Reynolds number and kinematic viscosity as RE equals velocity times dia by nu. First we will find out the velocity, and then through velocity we will find out the discharge, since the area or dia is given. So 2000 is the critical Reynolds number, velocity we have to find out, the dia is 0.01 and the viscosity is 10 to the power minus 6. So this will give us 2000 equals V 10 to the power 4. V will come out to be 0.2 meter per second. Now we'll find out the discharge. Discharge is given by pi by 4 d square. It is a circular pipe times velocity, so that will be 0.785 times 0.01 whole square times 0.2. Let's solve it on calculator for now. 0.01 square times 0.2, we get 1.57 times 10 to the power minus 5 meter cube per second. Now since 1 meter cube is 1000 liters, therefore discharge in liters will be 1.57 times 10 to the power minus 2 liters per second. That will become 0.0157 liters per second, which is near about 0.016 liter per second, which is our third option, that is C. Let's move on to the next question. Here we have another two questions. It says for the 40th question that there are two plates, parallel plates, of which one is moving with the velocity of 4 meter per second and one is stationary. So even in this case we'll have velocity profile. Okay, and we'll be using the Newton's viscosity formula, that is tau is mu du by dy, or which can be written as mu b by h, where h is the difference between the plates. The question is asking us about the shear stress on the plate. The mu here is given as 0.44 Pascal seconds. velocity is 4 and the h is 18 mm, which I can write as 0.018 meters. On solving, this comes roughly equals to 97.77. That is our A option. Let's see the next question. It is asking that the pressure gradient in the direction of flow. Pressure gradient is given by del P by del X is equals to shear gradient or the velocity gradient. Now this was a question that made me scratch my head. I was not sure about it. So the concept behind this question is that for a steady, fully developed laminar flow between two parallel plates, the Navier-Stokes equations tells us that this pressure gradient del P by del X is equals to del T by del Y, where this pressure gradient is parallel to direction of flow and the shear stress gradient is normal to the direction of flow. Hence the correct answer is shear gradient normal to the direction of flow, and the equation is nothing but Navier-Stokes equation. Let's move on to the next question. Here is another question in which somehow I was getting 16, but I did not go with option A. Let's go. We know that in a circular pipe, in a laminar flow, that U, the local velocity, is given as U max bracket 1 minus R by R square, where small r varies from r equals to 0 to r equals to r, where it is 0. The velocity is 0 here and it is max here, U max. Therefore, in this question what they have given us is the dia 4 centimeter, mu is 1.6 centipoise, which I can write as 1.6 into 10 to the power minus 3 Pascal seconds. Then we have velocity at the axis, that is U max is given as 2 meter per second, because this is the axis of the pipe, center line. Then the shear stress in midway between the wall and axis. This is your wall and this is your axis, and this is the midway, which is nothing but r by 2, y equals to r by 2. Let us see. So U is this. At y equals to r by 2 we will need U, so we'll find out U equals to U max, which is 2. 1 minus r is r by 2, so that will be 1 by 4, so this becomes 2 into 3 by 4, 1.5 meter per second. Then we have tau equals to mu minus du by dr, which we can solve as mu. When we'll differentiate U velocity with respect to r, you will get U max, which is constant, times minus 2r by r square. Therefore tau becomes mu into U max bracket 2r by r square, which is what we want. So we have r, small r 4 centimeter is our dias, therefore small r will be small r is where we have the question has asked us location, r by 2, so it will become 2 by 2, that is 1 centimeter, and capital R is 2 centimeter. This will be 0.01 meter, this will be 0.02 meter. So let's find out tau. Mu is 1.6 into 10 to the power minus 3 using this formula. U max is 2 times 2 into the radius is 0.01 and the capital radius is 0.02 into 0.02. This becomes 200. Tau becomes 1.6 into 10 to the power minus 1. Tau becomes 0.16 Newton per meter square. Now you see, we did not needed this. We did not needed to find out this thing. It was not necessary. We simply could have written directly that tau is mu max 2r by r square. Here are the 3 questions from SOM. The first question is the prop cantilever beam. It is a prop cantilever beam. It is supposed with a UDL of 2 kilonewton per meter on the whole span. L is 4 meter and it is propped at the free end. So what is the propped reaction? Now this is something which we all know, that reaction propped cantilever you've loaded with UDL is 3 by 8 WL. Therefore 3 by 8, W is 2, L is 4. You will have 3 kilonewton reaction. Okay, next question is principal stresses. Sigma 1 is minus 8 megapascal, sigma 2 is 10 megapascal. Then maximum shear stress tau max is given by the formula sigma 1 minus sigma 2 by 2, that will be minus 8 minus 0 by 2, that will be minus 8 minus 10, that is minus 18 by 2 minus 9. Therefore 9. No, since signs are not mentioned or nature. 20th is that the shear stress in a symmetrical I section. This is your symmetrical I section. So shear stress will be maximized. This is how it varies. At the junction of the flange section and the web section, there's a jump, and after that it further increases to its peak value, which is at the neutral axis. Since this is a symmetrical section, the neutral axis or the centroidal axis will be at one same position, so the correct answer is neutral axis. Let's see the other questions. Here are another question. We have another question. The 21st says that while analyzing the shear stress of the structural element, the ratio of maximum shear to average shear at the neutral axis of a circular section. We know in a circular section we get shear stress distribution something like this, and the tau max in this case is given by 4 by 3 of tau average. Hence A is the correct answer. And in case this was your rectangular, then tau max would have been 3 by 2 tau average for a rectangular section, and if it was a triangular, then it would have been 3 by 2 tau average but at h by 2, and at neutral axis it would have been 4 by 3 tau average for the same triangular section. And if it was a diamond section, it would have been 9.8 tau average or 1.125. Let's move on to the next question. Polar section modulus of the solid shaft. We know that polar moment of inertia J is given by Ix plus Iy. So for solid shaft we have pi d4 by 64 plus pi d4 by 64. This comes out to be pi d4 by 32. And now the polar section modulus is given by Zp as J by R, that is pi d4 by 32 by d by 2. This comes out to be pi d cube by 16. Hence D option is correct. Then we have torque transmitted by a solid shaft which is subjected to shear stress. Then we'll use the equation that torque by J is tau by R. So tau becomes tau R by J, which I can write as torque by J by R or torque by Z, just like sigma B is M by Z, very similar to it. The tau is given to us as 16. Torque is what we have to find out, and Zp, so torque becomes 16 times Zp, which is 16 times pi d cube by 16 gets cancels by, and dia is 100 mm, which what is the answer in, it is in kilonewton mm. So mm है तो 100 का क्यूब, so 3 into pi, this will be Newton mm, and kilonewton के लिए it will divide by 10 to the power 3, so it will become 1000 pi kilonewton mm. That is C option. Let's see the next questions. Here is another question. It says that the sum of normal stress in a compound stress system is constant. The concept is that in a 2D or a 3D stress system, the sum of the normal stresses on any mutually perpendicular, on any two mutually perpendicular planes is invariant or constant. That is sigma x plus sigma y will be equals to sigma 1 plus sigma 2 on any two more mutually perpendicular planes. So A is the correct answer. Let's move on to the next questions. Let's see these three questions. 25 says, if width and depth is increased, the bending stress, how will it be impacted? We know bending stress is given by m by z. This is your section modulus, which for a rectangular is given by BD square by 6. So if the width is increased, depth is increased, of course, sigma b will decrease. So B is the correct answer. Then which statements regarding the bending moment and shear force are incorrect? First statement says that the shear force is 0 at the free end of a beam. Let us assume that this is shear, your cantilever beam with a free end. Is the shear force always 0? No. Any external point here would impact the shear force. So this is a false statement. Now this is also the correct answer since they had asked the incorrect. Now let's see other points. Moment at hinged joint is 0. Of course, at any hinged joint, because it allows the rotation. So moment is 0 at any hinged or point joint or pin joint. Then there is moment is 0 at simply supported ends. Yes, any bending moment variation, point load or UDL will tell you that it is 0 at the simply supported ends. Then shear force and bending moment are maximum at the fixed end. Yes, shear force and the bending moment in a traditional setting are always maximum at the fixed end. So A is the correct answer. Then what is the correct increasing order of the following materials? Magnesium, alloy, cast iron, aluminium, nickel. Now this is more of a factual data based question. So cast iron's Poisson ratio is around 0.21 to 0.27, and for magnesium alloys we have around 0.29, nickel stands at around 0.31, and aluminium stands at the highest 0.33. Therefore we have to arrange it in the increasing order. The smallest one is cast iron, B, followed by magnesium, that is A, followed by D, that is nickel, and then aluminium has the highest. So A is the correct answer. Let's move on to the next questions. Here comes another question which asks, what will be the effect of stress on the stress due to temperature change, whether body will elongate, whether it will shorten. Now there is one ambiguity in this question, because often in these questions this term or this mention is important, that whether the body is restrained or not, because if it is free to expand or shorten, no thermal stress generates. But if it is restrained, the opposite thing happens. Like if the temperature is increased, it will try to expand, the restraint won't allow it to expand, so the stresses that will generate inside that body will be compressive, and the opposite happens. But in this case, since nothing is mentioned, we will assume that the body is restrained, and in this case the body will try to elongate if the temperature rises, but the stresses that will be generated would be compressive. Now second question is that 2D stress matrix is given, and we have to find out the maximum shear stress. Of course, we have sigma x as 50 and sigma y as 10 and tau xy as 15. So we know the formula from the Mohr's diagram is given as sigma x plus sigma y by 2 plus minus root under sigma x minus sigma y by 2 whole square plus tau xy whole square. So we'll simply solve it. 50 plus 10 by 2 will be 30, plus minus 50 minus 10 by 2 will be 20 whole square plus 15 square, that will be 30 plus minus root under 625, that will be 30 plus minus 25. Therefore sigma 1 will be positive 1, 55, and sigma 2 will be negative 1, that is 5. Therefore tau max will be nothing but sigma 1 minus sigma 2 by 2, hence 55 minus 5 by 2, that will be 25. Hence D is the correct answer. Let's see the 30th question. That in an error of 0.5% in the measurement of head in a V notch causes an error of. Now for V notch, we know dq by q is given as the error in the discharge is given by k dh by h. If it is your rectangular weir, then the value of k is nothing but 3 by 2. But if it is a V notch or a triangular weir, the k is given by 5 by 2, which will be happening in this case. So simply dq by q will be 5 by 2 into dh by h. So 5 by 2 dh by h is given. Error in the measurement of h is itself dh by h. 5 by 2 times 0.5%, so it will be 1.25%. Hence C will be the correct answer. Let's see the next questions. So let us see these two questions. The first question was stress strain graph for this material and this material. Let's see what we did in the A test. Of course, A would go with 4, where without increasing much stress, you are having a continuous strain. So that is perfectly. So A will go with 4. Hence these two options were, I had to eliminate out of these two. Second was this. It follows an elastic thing, then eventually it gets curved. So this was, the option was B will either be 1 or B will be 3. Since it did not got horizontal, which happens in perfectly elastic plastic case, so B would go with 1, that is elastic plastic. Then C, that is your 3 elastic, and because till here it followed the elastic pattern, then it went perfectly plastic. And then D will go with the rigid plastic. So B is the correct answer. Let's see the other question. It is saying that out of these 3 relations, which is the correct one? Now we have 3 relations between the the constants, the independent elastic constant or elastic constants. The first one is E is equals to 2g 1 plus mu, where E is Young's modulus, G is your shear modulus, and mu is Poisson ratio, which is often written as 1 by m also in some books. And then second relation is E equals 3k bracket 1 minus 2 mu, and the third relation is E equals to 9 kg by 3k plus g. So the first relation 2g 1 plus mu is correct, 3k 1 minus mu is wrong, 2k 1 minus 3 mu is also wrong. Therefore A only is the correct answer. Let's see some graphs here. This is ideally plastic material or viscoelastic or elastoplastic material. This is a perfectly rigid body because there is no strain happening. This is a nearly rigid body. This is an incompressible material. And then we have non-linear elastic material. Let's see some other graphs. This is a linear elastic. This is elastoplastic. This is perfectly plastic. And this is elastoplastic. This is ideal plastic. This is ideal rigid. So these are the correct graphs. And this is the graph of a high tension steel, high yield steel, and mild steel. We know as the percentage carbon increases, the ultimate stress increases, but the ductility decreases. Hence mild steel is the most ductile. Cast iron is a brittle, aluminium is ductile. Let's see the next question. Let's see another question, which is a simple SFD BMD question where we have this situation. This is our reaction, and we have a load UDL and 2 point loads of 50 kilonewton and 40 kilonewton, and then there is a centric load of 10 kilonewton also. Sorry, this is not centric actually, this is the UDL only. 10 kilonewton per meter, and the distance is 4 meters. This is 2 meter, and this is also 4 meter. What they have asked us is the moment at C. Let's first of all find out the reactions at A and B. This is your 50 kilonewton and this is your 40 kilonewton, and the UDL can be changed into a point load with a magnitude of 40 kilonewton WL 10 times 4, which acts at a distance of 4 meters. So this is RA and RB, and I'll try to just solve it quickly. The RA plus RB comes out to be 130, 90 plus 40, and using moment at A is 0, we get RA equals 80 and RB equals 50. Therefore moment at C would be nothing but, which is 2 meters, RA times 2, that is 80 times 2, that is 160 kilonewton meter. So D is the correct answer. Let's see the other questions. Here the question was that which of the following is true with respect to the point of contraflexion. The first point was that the point of contraflexure occurs for simply supported beam carrying point loads. So let us assume this is our simply supported beam which is carrying point loads, and since point of contraflexure is basically a point in the bending moment where the bending moment changes its signs, that is, it crosses zeros. This indicates a physical transition from sagging to hogging or hogging to sagging. Let's see the first case. How will our BMD be? The SFD would be something like this, and so the BMD will be something like this. So there is no point of contraflexure clearly. The first statement is wrong. Then second statement says that the point of contraflexure occurs when the shear force changes its signs within the span length. No, when the shear force changes its sign, you will get a maxima or a minima. That is, where shear forces change its sign, the bending moment is often maximum or minimum in some cases. So B is also wrong. Then the third statement says that the point of contraflexure occurs for overhanging beam subjected to UDL. Yes, in case of a overhanging beam and there is UDL, the bending moment goes something like this, and hence there is a change of bending moment from hogging to sagging or sagging to hogging. Hence C statement is correct. Let's see the 15th position. There is match of following. This will be solved through the simple fact that M by EI is equals to d square y by dx square, which is equals to 1 by r. Therefore M equals EI d square y by dx square. Now shear force is written as d by dm by dx, which can be written as EI d cube y by dx cube. Similarly, load intensity, which is written as dv by dx, will be nothing but EI d cube y by dx d4 y by dx4. Therefore shear force will be 2, loading intensity will be 3, slope will be d by dx, and bending moment will be d square. Hence B option is correct. Then 16th is that point of contraflexure will not occur in the case of simply supported beam loaded with a UDL and propped in center, that is, we have a simply supported beam and there it is having a reaction, so there will be a natural jump at that point. There will be no point of contraflexion, no change in the bending moment. Anyhow, when there comes a moment in between somewhere, there is a chances of jump. There might be point of contraflexion. Let's see the B statement, which says a propped cantilever loaded with a UDL. Now in a propped cantilever also we have something like this. If there is no reaction, this will also not happen in here. Then we have a simply supported beam which is loaded by UDL and a fixed beam with UDL. Now a fixed beam with UDL will have point of contraflexure. The question is asking us where it will not be. So when a propped cantilever with UDL comes, the fixed end has a negative moment and midspan has a positive moment, so contraflexure occurs. The question was asking where it does not. No, it occurs in this case. And when a simply supported beam by UDL and propped at center, there comes a negative moment over the center prop and positive in the spans, so contraflexure occurs here also. But simply supported just loaded with UDL, of course there is no point of contraflexion, so C is the correct answer. Let's see the other question. 17th question is simply asking the deflection and slope in case of cantilever. Deflection is given by PL cube or WL cube by 3EI and slope is given by PL square by 2EI. Hence B is correct. Let's see some other questions. Let's see these questions, starting from 10th question, that a load W is falling upon a bar from a height h extending it through delta, then the energy stored is. So let us assume that a load W falls over a bar from distance h and it extends it by h, that is by delta. Therefore the net distance through which it traveled would be, normally if there was no extension of the bar, it would have simply been h, but since the total fall this weight has had is h, along with, let us say this was the actual bar's cross section, by extending it meant it compressed it with a delta distance. Therefore the total distance moved would be h plus delta. The concept here is that the strain energy stored would be equal to the loss in potential energy through the weight, that is energy stored would be mg into total distance, that is work done, h by delta, that is w into h plus delta, and C is correct. Then property of the material undergoing deformation at a constant stress over a period of time is ductility. Let's see others. In case of a composite bar, This is aluminium and this is brass or copper. Load carried by different material. Actually, this is not a composite bar. I would say that this is more like a composite bar. The sum of the load carried by each, the total load is sum of the load carried by different materials. Yeah, that is correct. That if P is the load acting on the whole body or a composite body, they will deform as a single unit, and the total load share will be P1 plus P2, where P1 and P2 are the individual loads between them because they are rigidly joined and have equal initial lengths. Okay, so A is correct. Let's see this question. We'll first draw the stress and strain curve of a mild steel. It goes like this till the proportional limit, and that is how it goes. So upper yield, lower yield. For small values of the strain, the relationship is linear, yes, and the stress is proportional to strain until it reaches the proportional limit. Yes, this is a correct statement. If strain exceeds the proportional limit, the strain begins to increase more rapidly. Yes, it increases more rapidly, and the slope decreases. Yes, the slope also decreases. So both correct are the correct statements. Let's see these three questions. A composite section contains 4 different materials. Let us say there are 4 different materials, 1, 2, 3 and 4. Then the stress in all different materials would be, now there's a compatibility system in the composite sections, that strain will be same in all these 3. Now since stress is modulus of elasticity times the strain, even if the strain is equal, it will depend upon the Young's modulus of elasticity. Because they are different material, this will be different, hence stress has to be different. So fourth will be T. Then there is second statement which asks which are correct, incorrect. Brittle material is strong in compression, weak in tension. Yes, brittle is a brittle material easily fails in tension, so it is weak. Yes, this is correct. Ductile material is approximately equally strong in tension and shear but weak in compression. Wrong. Ductile material is strong in tension as well as compression, but it is weak in shear, so this is wrong. Therefore only statement A is correct. Then we have a uniform cross section area, length L and cross section A. What is the change in length? Delta L. It is simply PL by AE. That is option C is correct. Let's see the last 3 questions. Let's see the last 3 questions. In a tension test on mild steel on a universal testing machine, at which stage of the test should extensometer be removed? Ultimate stress, limit of proportionality, rupture, or yield? It is yield point, because the concept is that an extensometer is a highly sensitive instrument used on a UTM, and its purpose is to measure minute changes in the strain, and it is only designed to measure small elastic deformations accurately. Once the material passes its yield point, the strain becomes very long, hence it will damage a very delicate instrument, the extensometer. So we only use it till the yield point. Let's see this next thing. Identify the mechanical property. The property which permits the material to draw out longitudinally to a reduced section is nothing but ductility, and to make its sheets would be malleability, but here it is ductility. Okay, steel rod has an area, length, axial pull, maximum stress. Since they have mentioned that it is suddenly, so sigma stress is given by 2 times P by A. That will be 2 times load, 50 times 10 to the power 3, and the area is 1250, 10, 25. I can write it as this, 480 Newton per mm square. So these are the questions which I gave in the test series of engineering classes. Next time I'll upload the test FM-I plus SOM-II. in which we'll have first 4 or 5 chapters and the last 4 or 5 chapters. Thank you guys.